Yeah, good morning, everyone. My name is Long Yang. I'm a postdoc from the Oxford from the Vinodic GUANA group, and then I'm really glad to be here to present my recent research work on the PFAS destruction and fluoride use, and also thank you the workshop for the invitation. And then today my talk will focus on the phosphate-enabled mechanochemical PFAS destruction for the fluoride reuse. Okay. As we know that the fluorochemicals are very important due to their unique properties and they have a very great application in the pharmaceutical and agrochemical and lithium-ion battery and polymers. I think more than 25% market jobs and more than 35% agrochemicals that contains fluorine items. Actually, all these kind of fluorine items, they incorporate into the fluorochemicals, including the electrophilic and the nucleophilic fluorinating reagent. They are all comes from the fluorspar. This involves a reaction by treating the acid-grade fluorspar with the sulfuric acid under the harsh conditions to generate the hydrogen fluoride, which is a very toxic and corrosive intermediate. Although there are many safety, there are strict safety used for the HF, but there are still some HF spills accidents happens. So leading to the fatal accident and detrimental impact to the environment. To avoiding the use of the HF for the chemical production, our group recently developed some bypassing HF process to generate the fluorochemicals. This including by the using the phosphate mechanochemical process to activate the fluorspar for the fluorochemical synthesis, and also using the oxide-enabled low temperature activation of the fluorspar for the fluorochemical synthesis. Beyond the HF problem in the fluorochemical industry, the fluorochemical industry also has the issues related to the PFAS problem, and also has the problem of the finite global reserves of the fluorspar. So, this fluorspar, which already categorized very critical minerals by many countries to tackle to address the PFAS problem and also the finite resource of the fluorspar problem. And it would be highly beneficial to use the PFAS as the fluorinating reagent for the fluorochemical synthesis. So PFAS represent large family compounds, over 10,000 synthetic compounds. They have these PFAS could be divided into the polymetic PFAS, such as the PTFE and PVDF, and also the non-polymetic PFAS, such as the compound PFOA and PFOS. Owing to the thermostability, chemical stability, and the water-oil repellency, this kind of compounds has a greater application in our daily life. Such could be used in the non-stick cooking oil, and also the take-out containers, and also used in the firefighting foams. PFAS, also known as forever chemicals, because they are persistent in the environment, and they are resistant to natural degradation process, thus leading to the accumulation and bioaccumulation in the environment. So there are many studies prove that exposure to the certain PFAS can lead to the health effects, such can lead to the liver damage, kidney cancer, and even harmful to the unborn babies. So to address these PFAS issues, the EU has been for many years by enacting legislation to control the PFAS problem. A few years ago was a public consultation and the derogation process, and with aiming to 2027 totally ban all the PFAS, and unless derogation are in place. So in order to address the PFAS problem, there are many methods have been developed to decompose the PFAS, such as the oxidation reduction process and also the mechanochemical process, biodegradation, incineration, among other many techniques. However, most of these techniques that do not have recover the fluoride after this destruction, and probably because the complexity of the reaction system that makes it difficult for the fluoride recovery after destruction, thus leading to the fluorine waste that do not enter into the fluorochemical industry. So in this context, our group recently found that using the phosphate as activator, we can trigger the PFAS degradation to mineralize to the fluorine content to the fluoride and the monofluorophosphate, thus thereby enabling the recovery the fluoride for the fluorinating agent synthesis and for the fluorochemical synthesis. This approach is represent a general PFAS destruction method and also contributes to the circular fluorine chemistry. Actually, this is the serendipitous reaction was discovered when we using the fluorspar, meaning with the potential phosphate, and we generate the fluorine mix. And then we use this PTFE shielding for this reaction. And then we get after 3 hour milling, we get overstretched match fluoride release. This surprising result indicates that the Teflon was degraded under the mechanochemical conditions. So, as we know that the Teflon is a very chemical and thermal stability, and is almost constant degradation under many conditions. So this result is quite interesting and surprising to us. And then with this results, exciting result, we further screening different phosphate salt, and we found that the potential phosphate and the potential pyrophosphate, first, these two activators is very good activator, can contribute to almost all the fluorine mineralization to the product. With the potential phosphate, the major product is a potential fluoride, and while with the potential pyrophosphate, the major product is monofluorophosphate. Further screening the salt, and we found not only the potential salt, but also the sodium salt and lithium salt, they also can contribute to some of the fluoride release. For comparison, we also use the potential hydroxide and the sodium hydroxide for this reaction, but the yield is quite low. The reason why this kind of two compound has a low yield, probably because of the water formation during this milling process. The water can have a negative effect for the milling process, that's why leading to the low efficiency fluoride release. To further test the efficiency of the water, and let me use the hydrate activator for this milling process. Actually, indeed, water containing can decrease the reaction. And then during this reaction, we found the laser dramatic color change. At the beginning, the color is totally white. After milling 3 hours, the color changed to black. This change and triggered to us wondering what's the component after the milling, what's the exact component of this mixture. Then the next goal of our study is to identify the composition of the PTFE mix. And then when we use the potential phosphate as an activator to degrade the PTFE, we generate the PTFE mix PEF. To understand what's the component of this mixture, we use the solution MR to identify the carbon content and the fluorine content and the phosphate content. For the carbon content, the major component is the carbonate and the black carbon. And for the fluorine content, the major component is potential fluoride. And for the phosphine content, is the major product is a pyrophosphate. In contrast, when we use the pyrophosphate as activator, we can generate the PTFE mix PF. And this mix PF also can identify by the carbon MR, fluorine MR, and phosphate MR. The major difference including the CO2 formation, and the major product is monofluorophosphate when we use the pyrophosphate as an activator. Not only the solution MR, but we also can use the solid state MR to categorize this mixture. And then when we use the potential phosphate as activator, we can check the solid state fluorine MR. The major product is KF, and for the phosphate MR, the major product is pyrophosphate. And then for the pyrophosphate as activator, both the fluorine-NMR and the phosphine-NMR, the major product is monofluorophosphate. Then we further identify the composition by using the powder study of these two mixtures. We can clearly see that after merely 3 hours, these two mixtures do not have the starting material PTFE left and has a distinct crystal peak of the monofluorophosphate. Since during this reaction, we found there are so many byproduct source generations, such as the monofluorophosphate, carbonate, oxalate, and formate. Since the phosphate is a really good activator for the PFAS degradation, then we also wondering how about this kind of byproduct is that all this kind of byproduct also can trigger the PTFE degradation. So for to identify this hypothesis, we also using this byproduct source did the control experiment under this identical conditions. And indeed, we found that most of this byproduct can trigger the PTFE degradation, especially for the carbonate, can leading to the 75% fluoride release. To further understand what's the mechanism, what's the difference between this all different source and what's the mechanism of this milling process, we carried out the DFT calculations. First, we calculate the nucleophilicity of all this kind of salt, and we found the nucleophilicity has a positive correlation with the experimental total fluoride release, with the potential phosphate has the highest nucleophilicity. And then we further calculate the transition state energy of this SN2 process. And then we found that the transition state energy has a negative correlation with the experimental total fluoride release, with the potential phosphate and potential pyrophosphate has the lowest transition state energy. And then for the phosphate, the transition state energy is 30.9 kcal per mole, and the pyrophosphate is 40.1 kcal per mole. It should be notably that, as we know that this kind of polymer or PFAS under the mechanochemical conditions, it also has possibility to the homolytic cleavage. But the homolytic dissociation energy is around 90 kcal per mole, which is much higher than the SN2 transition state energy. So this energetic disparity supports that the possibility of the SN2 process. So with the best optimized condition in hand, we further test the generality of this reaction. We found that not only the PTFE powder, but also other polymers such as PVDF, PCTFE, and even the copolymer, ETFE, and the PVDF, HFP. And all this kind of material can give nearly quantity fluoride release. And then not only these fine polymers, but also the post-consumer materials like the PTFE tape and the PVF film and FEP film and the PFA tubing. And very importantly, when the PTFE mixed with some non-fluoride plastic, such as polypropylene, it also can give very high yield of the fluoride release. Not only the polymetic PFAS, but also the non-polymetic PFAS, such as the PFOA and also any other term covers as a PFAS, but also the PFOA and sulfur amide and sulfur amide salt, and also all the fluorotenomers. They also can work very well under these identical conditions. So since we can destroy all class of the PFAS, our next goal is to could we isolate, could we recover the fluorine content after this PFAS destruction. And then when we use the potential phosphate as activator, and then we generate the PTFE mixed cave, this mixture cave can be followed by a very simple extraction process with the methanol and ethanol. We can easily to isolate the cave and the high purity. The purity of the cave was identified by the NMR and element analysis, and also identified by the powder XRD. And then when we use the pyrophosphate as activator, we can generate the PTFE mixed PF. This mixture could be followed by hydrolyze with the hydroxide ammonium salt to generate the TBAF and TMAF complex. And also we can synthesize the TBAF complex. not only we can generate the fluorinating reagent from the PTFE, but we also can generate the fluorinating reagent from the consumer items and also the absorbed pollutants, such as the PTFE tape and the ETFE vial and the FEP tubing and also the PVDF fittings. All these kind of material could be subject to these milling conditions and give us quantitative fluoride release and isolate high yield of the cave. Very importantly, the PFAS observed on the activated carbon, these samples and also can subject to the milling process and give us quantitative fluoride release and isolate the high yield and high purity caves. And since we can isolate the fluorinating agent from the PFAS, and the next goal is how we want to use this reagent to synthesize the pharmaceutical or agrochemical, like we can synthesize the key structure motif of the lipitol, which is widely used for the cluster lowering drug. And also we can synthesize the agrochemical like the herbicide triaspirin and also the herbicide industrin. And also we can synthesize other very important pharmaceutical or agrochemical motifs. And not only we can use the cave for the reaction, but also we can use the untreated PFAS mixture after destruction directly for the synthesis of the deoxygenating fluorinating agent and also synthesize the electrolyte. So to make all this process more cost effectively or and more industry application, we next job is to conveniently cycle the phosphate after the PFAS destruction process. Then we have think that we can use hypothesis this cycle that phosphate degrade the PFAS to generate PFAS mixture, and this PFAS mixture could be hydrolyzed with the potassium hydroxide and release the cave, and simultaneously to get the recovery the potassium phosphate for the next cycle. And then for this, to test the feasibility of this phosphate cycle, we run 3 cycles for this reaction. And then each time we can get the very high yield of fluoride release and the high yield of cave isolation. And every time we can generate more than 95% of the phosphate for the next cycle. So to conclusion that as we know that all the fluorochemicals, including the PFAS, are originated from the fluorspar, and which is the fluorspar, which is non-renewable global limited reserve mineral. So we provide a new technique that using the PFAS as a fluorinating reagent to not only can upcycling the fluorine for the fluorochemical synthesis, but also we can recycling the phosphate after the destruction process. So with this, this project not only can contribute to the PFAS destruction, but also can contribute to the circular fluorine chemistry. So with this general PFAS destruction and coupled with so many other techniques that we can decompose the PFAS. So here I think that now the PFAS maybe is no longer equals to the forever chemicals anymore. So I'd like to take this opportunity to thank you, my supervisor, Professor Vinodic, and also thank you all my lab mates for their hard work and cooperation, and also thank you the funding support, Marie Curie and the ERC and the UKI supporting. Thank you.